All right, now we have an exciting lecture on the calculus of vector valued functions. I know, shocking, because you're in calculus, right? Okay, so we're going to talk about derivatives and integrals, and then we're going to, well, do some interesting things with them. But that is for another lecture. Cliffhanger. Anyway, derivatives of vector valued functions. So derivatives are defined in a very similar way as for scalar functions. Say what? Look at this. The derivative of a vector valued function r of t is, so we write r prime of t like we always do. It's going to be the limit as, let's say, delta t goes to 0 of r of t plus delta t minus r of t divided by delta t, of course, provided the limit exists. If r prime of t exists, then r is differentiable at t. For r of t to be differentiable over the entire closed interval ab, r of t has to be differentiable for all t in that interval. And so we have to define r prime of a and r prime of b, because at the endpoints, that doesn't quite cut it. So we have to say how we're doing things. So to determine the derivative at the left endpoint, we look at the limit as delta t approaches 0 from the right of r of a plus delta t minus r of a divided by delta t. And similarly, to find the derivative at the right-hand endpoint, we take the limit as delta t goes to 0 from the left. And so it goes. And so that's how we define the derivative. Practically speaking, we compute derivatives like we always did, right? We compute derivatives by differentiating the component functions, as shown in the theorem here. So it's just like we're taking limits, which kind of makes sense because we define taking limits component-wise. So when we plug in this definition of the derivative, we are doing that for each of the components, which turns into the derivative of each of the components. So we're going to use everything we already have learned in Calc 1. So if I would like to compute r prime of t for this function, as an example, because what's life without an example? We just do it component-wise, so we find the derivative of each component. So you should say it with me. Just pretend you're not looking at this by yourself, or maybe you're not. So the derivative of t to the 6th we know is 6t to the 5th. And the derivative of sine of 2t, we know by the chain rule is going to be 2 cosine of 2t. And the derivative with respect to t of negative log of the quantity t plus 1 is negative 1 over t plus 1 times, well, the derivative of t plus 1 with respect to t, which is just 1. And so that's our answer. And it turns out that most of the basic facts we know about derivatives from Calculus 1 still hold true with vector valued functions. So to make this clearer, boom. By boom, I mean, here's a theorem listing the properties. So we'll say R and U are two differentiable functions. F is a real valued function. C is a scalar. So the derivative of a constant times a vector valued function is the constant times the vector valued function. Addition, subtraction work as normal. We have the product rule, which works as normal. Well, we have the product rule when we're thinking about the multiple of a vector valued function times a scalar function, and the dot product. Notice that's a dot product of two vector valued functions, but check this out. It even works for cross products. So the product rule that we learned in Calc 1 basically lives on. Last but not least, we have the chain rule, which, okay, to be fair, I sort of already used a little bit, right? But if we have a function r of t and we kind of do the composition of that vector valued function with the scalar function f, boom, chain rule. We get a r prime times f prime. Awesome. So let's look at another example because, you know my philosophy. What is life without an example? So I want to find the derivative of the dot product of this vector valued function r with the vector valued function u. So I could do the dot product and then take the derivative, which sounds like so much fun, or we can use the product rule. And so I'm going to use the product rule. So first of all, what can we can do? We can find the derivative of our function r. And the derivative of our function r is going to be what? So the derivative of t cubed minus 1 is 3t squared. The derivative of e to the 2t is 2e to the 2t. And the derivative of cosine t is minus sine t. No, I have no explanation as to why I wrote that as a plus or minus. And we can write this in component form as the vector 3t squared, 2e to the 2t, negative sine of t. And we will rinse and repeat for the vector valued function u. So its derivative, so what's the derivative of the natural log of t squared plus 1? Use the chain rule. So we have 1 over t squared plus 1 times the derivative of t squared plus 1, which is 2t, that's times I, plus the derivative of e to the minus t, so that's minus e to the minus t, and that's times j, and the derivative of 4 is 0. So in other words, we have 1 over t squared, we don't have that, we have 2t over t squared plus 1 times I minus e to the minus t times j. And so in component form, this is going to be the vector 2t over t squared plus 1, negative e to the minus t, 0. Okay, awesome. So now let's use our product rule. Therefore, the derivative of the product of the dot product, I should say. So we know that's going to be the dot product of r prime with u plus the dot product of r of t with u prime. And I'm going to leave everything in component form. So r prime of t is 3t squared, 2e to the 2t minus sine of t. Dot product of that with u. U is the vector natural log of t squared plus 1, e to the minus t 4, plus r, which was t cubed minus 1, e to the 2t cosine t, dot product of that with u prime of t, which is 2t over the vector 2t over t squared plus 1 minus e to the minus t 0. So I'm going to get 3t squared times log of t squared plus 1 plus 2e to the 2t times e to the minus t plus negative sine of t times 4 plus from the other dot product, I get, wow, I sure do, t cubed minus 1 times 2t over t squared plus 1 plus e to the 2t times minus e to the minus t plus cosine of t times 0. When the dust settles, we end up with 3t squared natural log of t squared plus 1. We've got a 2e to the t minus e to the t, so we're going to get a plus e to the t minus 4 sine of t plus 2t to the 4th minus 2t over t squared plus 1, or however you'd like to write that. That's our answer. Phew. One more little definition. just in terms of general derivatives. We talk about a smooth function. So a vector valued function r of t defined on some interval a, b is said to be smooth if r prime of t is continuous on that interval, but moreover, it's not just continuous, it is also non-zero for all points on that interval. So the derivative is continuous and not zero anywhere. Now, as you may recall from Calc 1, when we talk about derivatives, we also talk about tangents. And as you've noticed in Calc 3 here, we're talking also about normals. But anyway, I digress. So we're going to talk about tangent vectors. So as you recall from Calc 1, the derivative of function represents the slope of the tangent line to the curve at the given point. So for vector valued functions, right, what are we talking about? So what's the tangent vector? So given the function r of t, given the vector valued function r of t, right, the tangent vector is the derivative right, r prime of t naught at a given point t naught. So that is the tangent vector. Oh, goody, we're having technical difficulties. So the principal unit tangent vector, which is usually just called the unit tangent, that is defined as the normalized tangent, right? We just normalize. So recall that normalize means that we divide by the magnitude of the vector. Okay, let's do an example. Let's find a unit tangent vector to the function r of t, whose components are t to the fifth, cosine squared t, and tangent of 4t. So first of all, we take the derivative. So what is r prime of t? You should try to do it yourself, but that's going to be the vector's components are 5t to the fourth. Derivative of cosine is going to be 2 cosine t times negative sine of t. And the derivative of tangent 4t, if you'll recall, that is going to give me a 4 secant squared 4t, which we can write a little more succinctly. 2 cosine t sine t, or 2 sine t cosine t, that's the sine of 2t. So I really have minus sine 2t, and that's the only one I can simplify. Then the magnitude of this is going to be the square root of the 5t to the fourth quantity squared plus negative sine of 2t quantity squared plus 4 secant squared of 4t quantity squared, which is equal to the square root of 25t to the eighth plus sine squared 2t plus 16 secant to the fourth 4t. And well, that's going to be fun. All right, so then our tangent, unit tangent, t is going to be just r prime divided by that. So I'm really not going to multiply that through. So I'm just going to write the answer here because, well, I gave us a less than pleasurable example to do, but that's life. Okay, so this would be our answer. All right. Normally, if we had a number, we would just multiply it in there, but we don't, so we won't. Let's do one more example. Let's find the vector equation of the tangent line to the curve given by r of t is t squared I plus 2 sine tj plus 2 cosine tk at the point t equals pi over 3. So first of all, we'll just take the derivative. R prime of t is going to be 2t times I plus 2 cosine of t times j minus 2 sine of t times k. So evaluating that at pi over 3, we're going to get 2 times pi over 3 plus 2 cosine of pi over 3. Cosine of pi over 3 is a half, so that's just going to give me a 1. And 2 sine pi over 3. Sine pi over 3 is square root of 3 over 2, so times 2 gives me square root of 3. Excellent. We also need to find out, we also need to evaluate our function at the point t equals pi over 3. So that gives me t squared, that's pi squared over 9i, plus 2 sine of pi over 3. We've already established that that is going to be square root of 3. And then 2 cosine of t times k, that's just going to give us plus k. So again, getting my computer to cooperate a little bit, this is what I get. So what's the vector equation of the line? Well, it's actually quite nice. I'm not sure I want to call it r of t, but the vector equation of my line is, so we have the point on the line, which is given by r of pi over 3, plus t times our slope, which is 2 pi over 3, the vector 2 pi, sorry, the vector 2 pi over 3, 1, negative square root of 3. That's our slope, and that's our line. I don't know what to give as the, let's just call it u of t. And that is the equation of the tangent line. Okay, this is long enough, so I'm going to stop. There'll be a very short video on, integrals next time.